and design engineering, project and construction management as well. CEI is the member association from India representing the Indian engineering consultancy for professions at the International Federation of Consulting Engineers, FIDIC, on the global forum. CEI has behind it over 60 years of accumulated knowledge and experience of two major consulting engineers association of India, that is Association of Consulting Engineers and National Association of Consulting Engineers. The main objective of the CEI promote professional interest and establish rights and privileges of the consulting engineering professions in India, represent the consulting engineering professions within India and abroad, connect the members locally and globally, disseminate among the members information and all the matters pertaining engineering, especially knowledge and information related to consulting engineering profession, act as a principal champion for consulting engineering professions by informing and educating the public and lawmakers about key engineering issues and have the voice of the professions heard by the policymakers. Promote adoption of equitable forms of contracts and other documents used in consulting engineering practice. Encourage settlements of dispute by conciliations, mediations, or arbitrations. Drive to get statutory recognitions of engineering professions. Future Leader Forum is one of the committees of the CEI, which was formed in 2012 with the intention of providing young professionals with an opportunity to participate in CEI, FIDIC, and Asia Pacific and interact with their peers and develop the next generations of leaders. The main objective of the Future Leader Forum is provide a voice of young professionals within CEI, strengthen the culture of dialogue, organize technical lecture in the science, engineering, and architectures, share success stories about young professionals, provide supportive space for young professionals to discuss and communicate, and enhance the consulting engineering profession all over the world. Now I am going to introduce moderator of the session, Mr. Ajay Singh. He is a civil engineering by qualifications and over the span of more than 12 years in experience. He has experience in structural design in RCC steel and PSC structures, rail and road over bridges, extra-doors bridges. He completed his postgraduate in civil engineering degree from IIT Kanpur. He is currently working in Doha Engineering Private Limited. Now I am handed over to Mr. Ajay Singh.
Thank you, Mehir. Thank you very much. Hello, everyone. I am Ajay Kumar Singh. Welcome you all to this webinar. Today, we learn about flow transition design in hydraulic structure. So, what is a flow transition? During construction of hydraulic structures such as aqueduct, bridges, hydropower intakes, and many other open section, the open section of flow is often reduced in order to economize the construction cost. So transitions are provided between original and reduced sections so that transitions may be broadly defined as that portion of a uniform channel undergoing a change in the normal prismatic section. Transitions are useful for reducing loss in heads and to ensure smooth flow without any disturbances. In this presentation, we discuss about the historic development of transition design and current design practices based on certain hypotheses which are not verified in India and abroad. This webinar is going to be very useful for civil engineers in working in infrastructure sectors. The next part of the webinar is around 65 to 75 minutes, which is divided as in next 5 minutes. I will introduce our guest speaker After that, our speaker will give his presentation for another 40 to 45 minutes. After that, we have a question answer session for around 15 minutes in which our speaker will answer your queries. So I request you all, please put your questions in question answer session so that we can read them together. Do not use chat box to put question answers. And after that, we have a vote of thanks by Mr. Asim Rastogi. So, not delaying further, now I introduce to you our guest speaker, Professor S.K. Mazumdar. He graduated in civil engineering from BE College Sipur, MTech and PhD degree in water resources from IIT Kharagpur. Professor Mazumdar has 62 years of teaching, research, design and consultancy experience in hydraulics and water resource engineering. He was head of civil engineering and dean faculty of technology, University of Delhi. He guided 30 theses at ME and PhD level, carried out several research projects sponsored by government, and authored 2 books in his teaching career. He has published 216 technical papers in reputed national international journals and conferences in India and abroad. He delivered several keynotes, lectures, and chaired many sessions on hydraulic and water resources. He has served as assistant engineer in irrigation and waterway directorate of Government of West Bengal, lecturer at IIT Kharagpur, assistant professor at RE College Durgapur, professor of civil engineering, hydraulics and flood control at the DTU, and visiting professor at Swiss Federal Institutes of Technology, Switzerland. He is a member of various associations such as CDC, CEI, IRC, and ISCA. Professor Mazumdar has been a part of various expert committees appointed by the government. Currently, he is one of the faculty member of Indian Academy of Highway Engineer. He is actively associated with formulation of Indian codes and standards. He got several awards in his professional career from various institutions like Institution of Engineers, Indian Road Congress. In 2009, he received Lifetime Achievement Award from Indian Society for Hydraulics, Pune, for his immense contribution in hydraulic and water resource engineering. So, not delaying further, I request to Professor Majumdar sir to start his presentation.
Okay, thank you, sir. Before I start talking on the topic flow transition, design and hydraulic structures, I wish to just mention that when I was a young engineer in the government of West Bengal Irrigation Department, I was in the design of hydraulic structures in a big irrigation project, in Gangshabati project. Anyway, so there I used to notice that whenever there is a change in head of my department, they used to issue a circular that now on we will not follow the previous transition design practice, we will follow this practice. Like that, 3-4 changes, heads change, government departments after 3 years. So I was astonishing that why they go on changing this transition shape, length, everything. That means that perhaps there is not much of fundamental design procedure. So with that objective, I resigned there because I was not very much interested in that organization, but I joined IIT, and as a lecturer, I was selected as a lecturer. So there I did my MTech and PhD both during my lecturership. And then my topic of master's thesis was transition. And in the PhD also, I took up more advanced area of transition, that is flow expansion. So my lecture will reveal that how I developed this idea and how I try to make some basis for the design. So with this background, let us share. So ये वाला करना पड़ेगा ना. Hello. ये second share दबाना. So buddy, ठीक है. ये वाला ना. अच्छा. So necessity of transitions. Transitions are useful for reducing loss in head and to ensure that the flow in the flume section is smooth without any undue disturbances. In online channels, if suitable transitions are not provided, vortices created at the entry and exit of the flume section create not only head losses but scouring of both bed and bands. Without proper transition, there will be non-uniform distribution of velocity, which leads to scouring and which requires costly protective measures. For example, when the normal waterway is restricted under an aqueduct, it is obligatory to provide suitable transition both at entry and exit to reduce the cost of the structure and to reduce the losses, and their losses means efflux, reduce losses and scour also, control scour. In case of a bridge, guide ones actually act as a transition structure. More is the loss in head, higher will be the efflux. Lot of problems like sediment deposition, non-uniformity of flow, instability of flow may occur in the absence of suitable design transitions. Additional protective measures like guide bands, embankments, spars, beaching, etc. They are needed to arrest those type of problems. In an intake structure for hydropower, for example, if suitable transitions are not provided, there will be a lot of problem like apart from head loss, because head loss means money loss. Vibration, cavitation, etc. In the desilting devices of hydroelectric plants, suitable transition at entry and exit improves the performance of the structure, ensuring greater efficiency. Now, this is a figure which shows the various parameters like D. These are, I am telling mean value, because if you have a trapezoidal channel, you can find the mean width. This is the approaching channel width, and this is the contracted width, where it may be very long also contracted, depending on the type of structure used. Just schematically, this is the contracted width, and this is the, if it is a weir with a jump, then this is a rise, and this, the top line, total energy line, is the chain dotted line, you see, which indicates the losses. The entry losses is HLI, then the exit losses, that is from here to here, is HLO. Then if there is a jump may not be there. For example, in aqueduct, you will not have jump, but in a fault structure where you have to make fluming, sometimes it is flume, there will be jump. So this is the heavy head, and then this is the normal kinetic energy corresponding to the normal depth. So this actually efflux is this level minus this level, that is called efflux. Well, in this is perhaps where here something. This is a schematic diagram. So now the next figure, because these are basics, I'm telling you that if energy has two components, one is called Y, that is the potential energy or depth. Another is kinetic energy, V square by 2E. So if you replace V in terms of Q by A, then for any channel, you can show, anyway, this is the graphical representation of the equation, that if you take the solid line, if you have got more discharge, the curves will shift to the right, and if you have less discharge, curves will shift to the left. This is called specific energy diagram. And you see that for a given energy E, specific energy E, there is only one depth, and that point, locus of that point is called critical depth. Any depth above that, that means this limb flowing, any flow or any flow other than critical, there are two alternate depths. One is called supercritical, low depth, Another is called subcritical, that is very low velocity and high depth, because that is the depth. Anyway, I don't want to go more on theory of this one. So, yes. Classifications. Open channel transitions can be subdivided into three groups as per the geometry by changing the width without changing the bed level. That is changing in the horizontal planes only, like Venturi type films which are used for measurement of flow. Aqueduct transitions, there is no rise in bed, only plan way. By varying bed level without changing the width, such as where speedways, may be contracted also. Speedways, yes, there may be contracted also. By simultaneously varying both bed and the both bed level as well as the bed width, that I showed you in the figure 1. Transition may be further subdivided according to flow regimes or flow flow condition, that is subcritical, supercritical flow, as I have illustrated in the previous figure. Now, I am discussing only this one, transition from subcritical to subcritical flow, with a little on the with the +3 at the end. I will give an example, subcritical to supercritical with a hydraulic jump that I will give you at the end. But most of the because I have written a book on this subject, transition design, same flow transition design by Taylor and Francis, but they are quite costly. But anyway, in 2020 it was published by CRC Press and Taylor and Francis. The book contains all types of, all different types, because the design will be different for different conditions of flow. Okay. Now, these are the different shapes. Now, these are the most of the, say, this curve may be a circular arc with the radius r in the entry. So these are given at the exit. So if you make the direction of flow this way, so it will be entry. This will be contracting transition. And if you come this way, then it is the outlet transition. So, this circular, you can have an elliptical curve. This is an oval shape, tangential at the exit and tangential at entry also. If this is a flow direction, this is inlet. If this is the flow direction, this is an outlet transition. This is called wedge-shaped transition. Gradually, because normally the channels are trapezoid also. You starts from a rectangle, and the structure is mostly rectangular, like aqueduct, and you can have it. And when you go this way, inlet, then it will be from a trapezoidal channel to a rectangular channel. These are called wedge-shaped. Now, in abrupt transition, also there are so many possibilities here. This is abrupt with an inclined wall. This is a sudden abrupt, or abrupt. This may be with a wall, side wall, or this may be a rectangular wall. So these are various types of transitions. Now, this Heinz design of transition in 1928, he made some hypothesis that the water level in a transition, that sounds subcritical flow only, composed of two reverse parabola, which can be used for determining the plant shape. So this design is very popular in USA, all European countries. But these are very costly. The length, axial length. When I say length, it doesn't mean the curve length. It's much more. So, and they are retaining walls, quite costly. So this length is about 5 times the offset. Offset is, say, this to this much, 5 times length. And exit also they put more or less 5 degrees. That is called 12 degrees 30 minutes from entry to exit, or exit from entry to from beginning to end, or from this end of the film. Same, but they are very costly. Now, and only for very costly structure they are used. Now, here is some, when I started working on this subject, I found there is really no guideline how to decide that how much you will flume. For example, in IRC code also, they say the breach can be constricted to such an extent that the efflux will not be harmful. Now, what is harmful? That they are not defining, or no degree they are giving. So this detail I don't want, but it was published in the Journal of Fluid Mechanics. So the ratio B0 by B1, that is the fluming ratio. B0 is a lower weight, and this I am calling only mean value. So this ratio can be expressed as a function of F1. F1 is the Froude number at the entry, and F0 is the Froude number at the structure, that is in the flumes. Where F1 and F0 is nothing but V by root Gy. That is a root GD. So that is called Froude number. So this function can be derived from fundamentals. Now, when you plot this function, then you get these curves for different. I found it for 4 different canals, in that department of irrigation, and found that when the approaching Froude number is very high. For example, normally the canals, open canals are designed not at supercritical flow, except in chutes. That is a different subject altogether. That is not in subcritical state. So when the Froude number is 0.432, you see that the opportunity to fluming is very, say for example, 0.52 only, maximum 0.7. You can have that much of contraction you can possible. But if the approach Froude number decreases, you see the opportunity of fluming becomes very high. For example, if the approaching Froude number is 0.005, very low velocity canal, then you can see you can contract from 0.1 to about, in fact, 1 you never do, because after 1 it will be choked, the flow will be choked, and there will be hydraulic jump. Where it is allowed, it's okay, but even then, it is not contracted beyond that. So best thing will be not to contract beyond, say, 0.7, because hardly there is any economy, whereas you were trying to disturb the flow, because if it approaches, before approaching the choking condition, the flow starts undulating. There are, and at this stage, the flow is completely full of waves only. Even in subcritical flow, there will be waves. So this disturbed flow is not desirable. So maximum of 0.7 to 0.75. So this method, and this paper was published. Anyway, now, these are the development Heinz developed in 1928. From time to time, USBR also gets some. There is a book for USBR. Jaeger developed a beautiful equation. Velocity function. He chose this A value and phi value. Phi is defined as this. In this y-axis is the depth within the, which Heinz has shown as reverse parabola. He said, nah, it values like this function. So phi is 1 minus A is this given, and then from this continuity equation you can find out the depth at any place, and then corresponding width you can find out. So phi is pi x by L. Yes, phi is pi x by, because it is my very old work. So anyway, still have. So Kulandeshami did some work. He worked before me. I went to IIT. Then before that, he did some work on transitions. Then similarly, CVIP has a very elaborate equations, alpha like that. Chaturvedi, that is a very popular transition at any distance x, how the width will vary. So this relation y and x given by, so these transitions have been used. Almost all hydraulic structures in UP, they call it Chaturvedi's expansion, contraction, like that. Smith and you, they developed certain baffles to use baffles, but there is considerable head losses in baffles. 1967, in my MSc work, I tested not contract, both expansive transition My work was mostly in working, contracting also I did, I think, I don't remember, now it is old, 33, 56 years old. Anyway. Now, Ishmael and Lebedev, these are he assumed that, for example, in a spillway, Ogi type spillway, or a dam, what is done, how the spillway shape is determined, that if you have a vertical notch and the water flow freely over the notch, they say that the lower nap is the locus of the lower nap will give you the profile of the Ogi spillway. Then there will be no separation of flow. That type of concept he took for the transition, that if there is a sudden expansion, so eddies will form. So what is the boundary? So if we make that was in vertical plane, he made it in horizontal plane, then what will be the equation of that separation surface? That is given by this equation. I use that equation for expansion. But first, in my master's thesis, yes. And the tan theta is, of course, the angle given. Then myself, and this I did with Professor Rao, who was the head of the department. In fact, he supervised my work. And we did a lot of work on how to, mostly our work on stabilizing the flow and on the improving the efficiency of expanding transition. So I told you about that. These are details, not only from subcritical to subcritical, it is given for all types of flow conditions. Now, this Ahuja, he was my student at master's level. So he tested Jaeger. He made very beautiful work, I have paper with him in many, one or two papers we have written together. So this, the loss equation, that Ci is a coefficient of inlet loss, which can be expressed as HLI, that I showed you in the first figure. And that can be expressed as 1 upon eta minus what is called inlet efficiency. So Ci, coefficient loss, and eta I, they're related. You can see that higher is the value of eta I, lower will be the Ci value, or opposite. Ci will be. So similarly, Vittal Chiranjeevi, they have also used a function to determine the transition shapes. Now, coming to flow characteristics in subcritical transitions. In contracting subcritical transition, there is a fall in water surface that you have seen in figure 1. There is a drop. So the water surface level down. That is in subcritical. Supercritical is opposite. So therefore, the transition design in supercritical flow is not so easy. I worked 1 year in Swiss laboratory. They invited me because they told we are recognizing your work at subcritical transition. You come here and work on. So I did 1 year work, and I think we had about, myself and other 2-3 people. We had about 4 or 5 papers in ASC, then IAHR. They are international journals. Anyway, pressure distribution this is only for subcritical flow, is non-hydrostatic due to curvilinearity of flow surface. Velocity distribution non-uniform, as the flow is 3-dimensional, varying resistance at the bottom. Additional complications arise when main flow separates from the boundary, resulting in backflow and eddies. Analytical treatment of such flow is extremely difficult. I have not seen any analytical work so far on the transition. Aajkal to hydraulics mein bahut analytical, that is called, that because of the computer advent of many equations like Prandtl-Kalman or other sophisticated equations has been now solved, so that particularly in the field of flood analysis, where using numerical analysis has been adopted, but transition is very difficult subject. So I'm not saying any. So my work was all experimental work. And what I'm going to present is experimental research results. In expanding transition or simple expansion, what happened? Hydraulic gradient is positive because there is, but in supercritical flow it will be opposite. So hydraulic gradient is positive, or adverse pressure gradient in subcritical flow, as there is a rise in, like in aqueduct or other two-dimensional flow. So boundary layer equation by Prandtl. Prandtl is the father of modern hydraulics. He is a German scientist, Sisting also. He has got a very big book on boundary layer. So from there, I'm just taking only one equation. dPdx is for pressure gradient or pressure gradient. dP is the pressure gradient in the direction of flow, can be written as mu. Mu is coefficient of dynamic viscosity, and d2 dy is the curvature of the velocity profile, and dPdx that I have proved. So now let us. Here you can see. Well, if I take a circle, because I made it approaching straight, and let us say this is an expansion going like that. So what happened at one point, because the boundary layer thickness increases, it can be proved that the boundary layer thickness from the dotted line will increase. Initially, the boundary layer thickness may be very small, but then it increases like that. And at one point, that point is called inflection point P, when their curvature is 0. So from there, this is called separation stream and free stream tube. So this will be the shape of the velocity profile. So under the influence of the positive pressure gradient. So hydraulic analysis of expansion in subcritical flow is more difficult compared to the contraction. In subcritical contracting transition, pressure energy is converted to kinetic energy flow, and the process is stable. Whereas in expanding in subcritical flow only, in expanding transition, however, the kinetic energy is converted to pressure energy, which is an unstable process. In an ideal transition, there should be minimum of head loss. Higher the head loss, less will be the efficiency of transition, and vice versa. Based on the above concept, it can be proved that the efficiency of contracting transition eta I and the expanding eta O can be expressed as eta I 1/1. What this is called coefficient of head loss. People, because in US we are designed, they have used only CI and CO anyway. So now eta, this can be expressed that 1 minus CO. CO is the outlet coefficient loss. Higher is the loss you find, less is the minimum, and higher, lower is the head loss, more will be efficiency. So figure, I have got two figures. So here you got, it's a contracting transition. You see that this is the average, it is a contracting transition, but these are called average axial length, axial length of transition, 1:1. You see the efficiency is poor, but if you come to around 3:1, you see this is 3. It's very high. So maximum efficiency of 94% occurred at about 3.3:1, and the minimum corresponding point was minimum CI loss was at that point. So therefore, we concluded there is no use of making longer length, axial length, like Heinz beyond 3:1. Why should we unnecessarily spend money? So that was our conclusion. So, for example, in my master's thesis, I studied so many things. You see, these are different curves, cycle, which is popular in UP. Then Chaturvedi's curves. These are all from those equations. And this is the type of Heinz type condition. And then this I tested. So you will notice that in all these transitions, when we tested, that maybe Heinz transition where this is Heinz transition. Well, the extent of this separation, and you see that the distribution of velocity at the exit highly non-uniform, thereby resulting in scour, because if the flow doesn't diffuse over the whole width, then the mean velocity will not be what we assumed in the design of the canal. Somewhere it will be even 2 times. So that will cause scour. Or it may be on the other side. It may be unstable also. The whole jet may go that way. So this is the eddy shaped expansion. I told you east-west Lebanon, which I tested at master's level, that how we compared the values, how we perform this flow. And these are some of the works I told you, for example, baffled by, but there is absolute head loss, but so diffusion took place. Then this was Mr. Rao at when he was the chief research officer at Warangal, Gindi Research Station. He developed a, this is the thickness of the wedge, wedge-shaped expansion, which diffuses, but he didn't develop any how to design that. That was not there. Just there was no design procedure, and this is a type of these are appurtenances. This is by Cochrane. Cochrane did a lot of work for flow diffuser. So he said that if the whole channel can be divided into 1, 2, and 3 channels, then there will be no separation, because separation occurs at an angle about 5 degrees. So that is total angle about 10 degrees. So therefore he divided, and these veins are very long up to the end, so quite costly, but their performance is better compared to this smooth. They are all devices, and we developed this. I'm going to we develop triangular veins in my PhD work. This develop the veins. I will just discuss how to. This was the work at the PhD level. Now, this is a comparison of efficiency of that I told you. This is Jaeger inlet transition. Optimum length is, axial length is about 3.3. But even if we make 3:1, hardly there is any change. I recommend that even 2:1 is sufficient, because hardly 2% loss in efficiency. It doesn't matter. But beyond that, if you make then there will be heavy addition process. And in expansion, you see, what happened, the maximum, this is only true for the that eddy-shaped or east-west logarithm curve, which I tested. It comes to 8:1, because up to so many models I have to make 10:1, up to 10:1 or 12. Anyway, so the maximum head loss, the maximum efficiency occurred at 8.1. So you see how much is the cost of the experiment. Then that's why we thought of that. As far as contraction design is concerned, you can adopt any curve. You see, it may be a elliptical, or it may be a but it should be tangent at the entry to the flow. That should be tangent. That, because in a high velocity area, you should not have some abrupt contraction that will cause more losses. So that is okay. Of course, is that Jaeger transition was very, very good transition that we recommended. So, and in expansion, to get the maximum loss, you see the length required is enormous. So here I want to just discuss a little bit of what is called. This is of course not for a aqueduct. This is called jump type. Say a canal fall, the water is coming with a high velocity. These are on the contracted position, and the hydraulic jump occurs up to this. This is the end of basin. Up to this, the sidewalls are parallel, and jump occurs, and the flow diffuses because of this roller that helps in diffusion flow after the jump, and then the normal depth occurs. This is actually the ideal thing, that if this is the energy loss, total energy loss from beginning to end, that is the upstream energy, downstream energy line to upstream energy, which is a summation of this, that is head loss at entry, exit, all these things. So you see that this is the transition portion. So, if you have this type of a basin, that means if the energy loss is represented by this, if the energy line is this, then all losses required in the jump are dissipated in the jump, and you will have the normal flow right from the exit of your structure. But it doesn't happen. So actual energy line happens like that. That means the kinetic energy is flow from here to here. That is called, what hydraulic jet length, energy length, that much. So residual energy is this much. Now, one may wonder that that when there is so much of energy loss in the jump, why you bother for this? Well, this residual energy, it may, because here the kinetic energy of flow is small, very small. The kinetic energy means v square by 2g. That is maybe 0.01 or so even if 0.05 of kinetic energy goes undissipated, that creates a lot of flow distortion. Because next figure you will realize that. So you see here, the flow, same flow in a channel may pass either as a rectangular distribution of velocity, rectangular, or this one dotted. Well, the mean of the three, that is the area under the velocity diagram, is the flow per unit width. So the flow remaining same, depth remaining same, depth and flow remaining same, the only way the residual kinetic energy can be contained in a flow, that is through distortion. This also I have papers, 2-3 papers. So published in very reputed journal. So this there will be backflow and there will be concentration of flow. This is in elevation and this is in plan. How the flow, there the flow is same, depth is same, but a small amount of kinetic energy remaining. So recently I read a paper in Misr, Egypt. There are several barrages in several places, and they noticed that there is a lot of scour after the barrage. So one reason I wrote a discussion of 3 pages, and I wrote that that this is all because of the residual energy. Because what happens in barrage, when there is lean flow, they open one gate, or is little hard to open 2 gates. So out of 20 gates. So these tests they made, they found that they made in the models 10 gates. When only 2 gates are opened, they found the scour is very high. And when they open 10 gates, then they found that this scour is almost nil. So that they couldn't find the reason. So the reason is this, that when only 2 gates or 1 gate is open, the flow doesn't diffuse and the energy loss is not complete. Because in the model study, even in research station, I have asked them, they have also commented that they test for full discharge when all the but not for 1 gate opening or 2 gates. Because the highest plant, when highest plant occurs, all the gates are opened, and then there will be not much of problem. But the problem occurs when you partially open the gates or few gates are open. And this is a problem of loss. Even in expansion also same thing happens. Now, the experiments we conducted in a very big flow, because those facilities are available in IIT. So that I'm not going to show you. But here in Delhi College of Engineering, to understand the flow behavior in an expansion, you can see this portion, contracting portion was fixed, and these 2 were hinges. So what could be done? I could, and this width, this is the channel wall. This width I could control to V0 or B, capital B, एक ही बात. Anyway, this diagram I've written to V0 means B capital B, and this is too small. Oh no, this is same. Only this is small V0. V0. Oh, there is a mistake here. That means too small B. Anyway, so this angle is called the total angle of expansion. Half of that is called. So what we did, we tested how, supposing I bring this point here, and then the width will go automatically less. That the study objective was how the expansion ratio, that is the small width versus the bigger width, or big versus small, as well as a rate of expansion, that is the length of the wall. How does it affect the flow stability and the losses? So I will show you. This was fabricated in the laboratory itself. Well, in experimental work, unless you have some, in Switzerland, I remember every model had to be built by me, because they had mechanics only one or two, they will come one or two drills. Okay. Oh, no, resting. I said, no, I don't know drilling. So of course, we had a course on drilling in our underway, but normally you do not take it seriously. So anyway, but there, the research worker have to do their own modeling. They have to do, they have to. Anyway, so that's why I say all the people that, you old people cannot do much of research because your energy goes now. So young people, unless young people with some motive for research joins. I have seen that in IIT Kharagpur in my time, there were 6, 7, then there was a lot of work going on. Today, IIT, I don't know, I'm not much in touch. But in earlier days, I have seen there were a lot of people. In Swiss laboratory, at least 18 people, various aspects they are studying, only more experimental model studies they were making. So you can see in this picture that when the angle is small, say 10 degree, 5 degree each, there is no separation. The flow will be smooth. If you increase the angle further to theta, say 10 degree to 20 degree, then you find some transitory eddies. These are called why transitory? Because they appear and disappear, and it starts from this end because boundary layer is very thick here. That's why it starts separating. And if you make further increase, say 30 degree, 20 to 30 degree, then you find that one eddy, this is called fully developed eddy. They will very long. Even it will go say 500 meters down, like that, very big eddy. And this is a reverse flow. Eddy flow will be there. There will be a lot of loss. And if you make further increase, say 40 degree or 60 degree, then what happens? There is a jet. The flow will go like a jet. With one side will be fixed, maybe 400, and this may go for 4 kilometers. So these areas with highly non-uniform will undergo erosion and lot of disturbance. The bank will be eroding. So because of these waves, so this may happen. So anyway, variation of instability with expansion parameter. So we develop two parameters. What is IA average and S? I'm just showing you. IA average is the one by is anyway delta E by L. I show you what is delta E. Delta E is nothing but if the axis of the maximum flow is by this line, if it is maximum flow occurs here, because velocity distribution normal also, it will be like that, so the maximum velocity will occur, then it is a very good case. But if it moves, the maximum velocity locus, if it moves, that is called delta. And L is the length. This is the B and this is the small b. So you see that here, yes. So we found these are only to explore the eddies, that how it develops, disappear like that. So we found that the 4 parameters which are very important in this, they are Froude number, then Reynolds number, aspect ratio, and the expansion ratio and expansion angle. Well, first 3 parameters doesn't have much of effect. Then we concluded that it is the expansion ratio, that is the ratio of pluming ratio, एक ही चीज है, and we did it for expansion only, because expansion is a big problem, and expansion rate at which you are explaining. So these 2 parameters we explored further and found that how the I instability changes with expand. This is L by 2B0 is the expansion rate, and these are the expansion. Oh, this is S, yes, that parameter, how it changes. So you see that this is the change over the maximum occurs somewhere here. And next figure, you will see how the efficiency varies. So these are the various expansion rate, and then and this is the angle. So if more is the angle, you find that the efficiency is very small, and it will be something maximum height here, in maximum height 10 degree, it's around 10 to 15 degree, okay. these are eddies. These have to be determined. We had tracer by which we could find the eddy length. So eddy length also this is the non-dimensional length. Just expand. You divide eddy by L by the length of the expansion by b by small b minus b, and the lengths are different in two sides. And more as the angle, more will be the asymmetry of flow. Now, these are the study made in a diffuser. Diffuser means in case of a say a tunnel type of in closed conduit flow. Closed conduit flow. This is the work of Klein. Klein did a lot of work. So he found that these are all just conceptual things. They found that below this line, the flow cannot separate. 2 theta. It varies from 20 degree to depending upon this value. That is rate. So he found this one, and these are called transitory eddies. In that region, it is fully developed eddy, and this was for closed conduit pressure flow. But in open channel flow, we found almost same thing, but it is varying, depending on flow velocity, depending upon discharge also, but more or less same regime, more or less same regime occurring. Now, economic and efficient design of contracting elliptical or contracting elliptical quadrant or cylindrical quadrant shape with center line with the curved line on the entry tangential to entry, yes, at the throat section will suffice, because for or trochoidal is a curve which you can generate if you have a bigger circle moving, and within that you just draw a small circle, and if the outer circle rolls on, then that inner circle will develop a curve which is called trochoidal curve. So they are quite sufficient, not because they are very small flow. Performance of contracting transition by Jaeger's type curve profile, which is tangential, and that equation is very powerful, and we found that is very good. So this was done by Mr. Ahuja. So it was 94% at 3, and hardly 92 at 3:1 to 2:1. It varies from 90 to 92%. So we have recommended that adopt a curve of Jaeger's type or any. It depends upon you, but no need of making 5:1 or 6. It's not needed. So it rather reduces efficiency. Then some small amount of flow separation occurred at entry with the contraction when the length is shorter than 2:1, resulting in head loss and fall in hydraulic efficiency. It is therefore recommended that average 2:1 may be adopted for the subcritical transition of Jaeger type profile. Longer length defined by an average side slope of 3 from the other end is not only costly but hydraulically inefficient too. There is no need of providing such a long transition as recommended by Hines. Performance of classical expansion. So in my PhD work, I concentrate mostly on this, expanding transition. Exhaustive study of addition with expanding transition using Ishbert and Lebedev type profile was studied with different axial length varying from 1:10:1. I have shown you earlier. Performance of expansion were measured in terms of following parameters: hydraulic efficiency, eta O. This is called the Coriolis coefficient alpha, that indicate the distribution of the velocity. Alpha is equal to 1 means completely uniform rectangular distribution, and alpha is equal to 3 means highly. In case of a hydraulic jump, if you take within the jump region, it may be even 40-50. So this is an indicator for the distribution of velocity. And then another parameter, that is standard deviation of actual bed shear distribution with respect to normal bed shear. If the velocity distribution is uniform, you will get a bed shear, because the distribution of velocity and bed shear are related. So that parameter is called sigma. So smaller is the value of sigma, it is preferred. In fact, you can see in this case, if C0 or coefficient of velocity efficiency is almost 100%. And U this is the U cube dA by A V cube. A is the total cross section and V is the average velocity. Now U is the local velocity. Now if U is equal to V, then it becomes the V cube, and V cube will go, it will come outside, and because this will be cancelled with this, and integration of dA is nothing but A, so alpha will be 1. So, our attempt should be to achieve 1, even in normal flow, it will be not less than 1.07, 1.12, it is not. And sigma is the, if tau x at any point x and tau n is the normal shear stress, then this value is 1. Supposing it is normal, then 1 minus 1 is 0. So then this becomes it. So we should try to get sigma as near as small. It cannot be possible. Even in normal case, it will be not less than 0.15, 0.2. It's not possible. Because this tau and U star is nothing but tau zero. U star is there nothing but these things. These are derivation you can easily derive from Prandtl equation. So these are the expression for the U star. From there, you can, from measurement of velocity, you can calculate the shear stress, and then you can determine sigma value. But you must have very good measurement, reliable measurement. Performance of classical design of how much time I have taken? It is 12:30. So I think I have got about, when I started, 12:05. Oh, sorry, it is, oh, my time is over. 1 hour. Okay, I'll quickly glance through. Such long length is not only costly, it is inefficient too, since the hydraulic efficiency is very poor and separation at exit and non-uniform distribution occur. So these are the design of subcritical efficiency is found to be 75. I told you all these things. And this I think I can skip. Then boundary layer flow control devices, that also I have to. So I forgot. Now, this is the triangular vein. I will show the vein shape is triangle. This is the A, but there, and this is the length of the vein, and this is the shape of the vein in elevation. This is in plan, and the peak point, this is the maximum height of flow, and this location is 2/3 length and 1/3 length. This took me 1,200 experiments to find out this vein geometry. So I will just show you, because time is over if there is. So this I have already chosen. So these are the experiments from which we can determine. You see, without vein, what happens? The shear stress distribution. Look at how concentrated, there will a lot of stubborn. And with vein, you see, they are controlled. This is the separation without vein, and this is with the triangular vein. So this is the standard deviation. So only one figure, one typical. So these curves can be used for determining the various, that is, you can see that discharges are there, but this is for determining length of the vein. From the point of view of, they are almost where the efficiency is maximum. I have seen the standard deviation also is minimum. So it's good. So that satisfies the relation. So from such studies, I don't want to. So you go in the depth, these are given in detail in the book. So here, the design curves, the question is how you design. So in the book, I have given these are model discharges and model found number, but you can convert it to the prototype discharge. Quite a large discharge that is applicable. So you can, from these curves, you can find out the length, the veins, in fact, I'll show you this. Yes, they are not attaching the wall. There is a small gap. So U is the distance from the outer edge of the vein, say concrete vein. So you will have U at that distance from outer to outer. So it is not exactly B, small b. So these curves help in determining their design parameters. Okay, and this have been compared that how this ends. So these are all classical. Heinz is this one, almost that triangle, and this is triangular beds. That's why I have triangle. this is triangular vents. Triangular vents, these are for large discharge. Here, I think one point is, I think that is perhaps anyway, for large discharge, only you can go for this type of lines and like that, but they're very, very costly. Okay, so yes, these are the pictures of, the without when you see the whole jet coming on one side, and these are all occupied by AD. And here, the whole flow is diffused. This is only aluminum powder. There is no separation actually. Actually, I told him to take the photograph after the, but he couldn't take it. That because photography at that time in Switzerland we have they used to use cranes, for taking photographs. I have taken myself. You will not get any help. You have to do everything there. I was much younger. And this is the distribution. You see, without hand, you look at these are already very highly non-uniform, and these are more or less uniform with hands. These are the scour, you see, without hand, a lot of scour, and there is no scour, absolutely no scour. We presented the paper in Institute of Engineers India. Myself, I was the main author, and Professor Rao, second author. We got the gold medal for our work by the Institute of Engineers. And this concept, there is another. So in Delhi College of Engineering, after I joined as a professor of hydraulics and flood control, I used another device to control separation. In any expanding, say, straight expansion, how does it differ from a hydraulic jump is occurring where the stealing basin is straight up to the end of the basin is this. So it will be straight. But here it is. So what is the difference between the straight wall and an expanding wall? The difference is this. If you take the reaction, that is the thrust given by the wall, if you have the momentum relation, you see that the P has two components. One is forward direction and another normal. So they are cancelled. These are on the two. But this PX and this PX add. So the forward force acting on the free body diagram will be 2px. And if you can control it by giving an adverse slope, because adverse slope reaction will be F normal to the weight, and it will have Fy and Fx. So Fx, if we can make equal to 2px, let us see what, and we got that was published in a German paper, German conference, and they were very much appreciated. So this concept has been, and we derived this equation, the values of this. So what is the angle? This angle also we derived. Alpha is nothing but the ratio, and D1 and D2 are the conjugate depth ratio. This is the curve. So this is there is some difference, but more or less these are that equation, and these are the experimental results. So there is some difference, but more or less is fine. So this type of curves can be used for finding out the optimum. So this optimum slope. So in a recent paper in in an inlet transition for the hydropower, I suggested this type of, because there is in our present design practice. So one chairman, Central Water retired, he wrote me a personal letter, Dr. Mujumdar, your paper is excellent, and we want to further test it. I said, you can test it because they have access to big laboratories, So because after all, flumes in laboratories are not, you cannot make, so they can be tested on a prototype. They can be in small canals. They can be tested. There is nothing wrong in that, because after all, in doing anything new, you should be very sure that this works. So, what is the economy? You see, I'm telling you, in a traditional canal fall. You see, in a traditional fall, this wall will be same length as this. But anyway, in my case, the solid line is the recommended that you take a very sharp contraction, 2:1. Then you have a, say, aqueduct or any structure, and have an expansion in 3:1. But in the classical one, you have to make this wall up to this, because the jump should be, otherwise jump will be special. So they do not know how to design for spatial domain. I have got the method. So anyway, so up to this, and then a transition, if you contract, so look at the cost of the structure. This thickness also will increase. So you can reduce so much of cost by, they are all walls, retaining walls. So much of cost. So I think that's all. Any other questions? I'm sorry, it went beyond my given time.
Thank you, sir. Thank you very much. It's us. Thank you sharing your work with us. It's a very informative presentation. So now let's move to the question answer session. If anyone has any query, please write it in chat box so that we can discuss with Professor Majumdar. Uh,
I think I have consumed the question answer time.
no, no, sir, it's fine. We still have a time. Anyone, please write in the chat box.
Or if there is any question, I can be, because I have got an email address. You have got that. People can contact me also.
Okay, okay.
Some consultancy from my home, because now I'm very old, 87, but still companies are coming, approaching me, including your ICT, Mr. Singha. Mr. Kapila told me, yeah, we have a big breach. Why don't you come and join us? I said, no, I can't. So then, okay, we'll send your engineer to you. So like that, I have done 4, 5, or recently another brilliant structures, Mr. Bhaumik. He had a big problem of scour determination. So one engineer, I told I will not go. So you send your, I will train him and see that your department is equipped to it. Because hydraulics is not everybody's cup of tea. And in undergraduate level now we teach very less. But postgraduate, we teach much more.
So if anybody don't have any question, you can also send your question to. Okay, there is one question. How do your model result compare with those of FCD, which would be more prevalent nowadays?
How is it compared with what?
How do your model results compare with those of CFD, which would be more prevalent nowadays?
CMT is full name means?
Can you, Mr. Arun, can you tell us the full form of CFD?
Oh, computational fluid dynamics. Okay. No.
Yeah.
I told you, computational fluid dynamics is nothing but numerical analysis. It is such a complicated, particularly expansion. In contraction, as you don't know, I have not done that. Well, I have very little knowledge on mathematics. Mathematics, whatever is needed for my model, that much I knew, and that much I learned. The understanding basics is very important. Fluid dynamics, yes, computer is very advanced subject, and I definitely encourage if someone can, even contraction, you can do that. Very good. It is. But I think in expanding transition, it is because there are so much of complication due to boundary growth and separation. I don't know. Maybe that is also possible. Thank you.
There is no more questions. Everyone, you can also share your question with the CIA or with sir. We will put the email address. So now let's move to the closing remark. I invite Mr. Asim Rastogi. So let me introduce Mr. Asim Rastogi to you. He is a civil engineer by qualification and over the span of more than 10 years of experience in the field of bridge and structure design. He completed his civil engineering from Allahabad in the year 2010 and post-graduation in MTech structure from BIT Misra Ranchi in the year 2013. He is a permanent member of the Institution of Engineers and the Indian Road Congress. As a structure engineer, he successfully completed many construction projects, which include DPRs and construction projects in India and in abroad. He is skilled in all phases of engineering operations and have vast experience in designing of PSC, RCC, and steel structure with shallow and deep foundation. He successfully completed the design project in Myanmar, Tanzania, Democratic Republic of Congo, and Bangladesh. So now I invite. So now I invite if to Mr. Asim Rastogi to give us a closing remark.
Thank you, Ajay, and good evening, everyone. It's been honored to be the part of this webinar series. And on the behalf of CAI and Future Leader Forum, I also like to thank Mr. Professor S.K. Mazumdar, who is a well-known person in the field of hydrology. And sir, your experience and guidance helps a lot of students and engineers. And as for today's webinar on the flow transmission design for hydraulic structures, we need to look into the importance of transition design, because nowadays every engineer just looking for the design of structures only. They did not give much importance on the hydraulics. So as an engineer, we have to look the hydraulic part also. And sir, thank you for your details and your experience. And we will like to know everything and more about on this topic from you later on. And by this, I like to thank Mr. Mihir and our moderator for today's session, Mr. Ajay, who handled the event throughout. And but not the least, I also like to thank our participants who gave their time and helping us to make the successful event. And this is all from my side. And thank you once again.
Before you just stop, I will, if possible, organizations can have a copy of my book, because I have given some 6-7 design of supercritical to supercritical in bridge. You know, our existing guideline design is totally wrong. IRC may I have put in, and they are going to change. They have already changed IRC 89, because more you film, the longer will be the length of guide one, but it is just opposite. Here they say that is, if the length of the bridge is L, then the upstream length of the guide one will be L. That means, smaller is the length of the bridge you require in a wide river, then smaller will be the guide one length, which is totally wrong. So this has been changed in the 89. I was actually one of the Mr. What is his name? Mr. Sharma was the chairman in that. Because they have, I am still working in that groups. We are now going to have a book on, not book, a code on only bridge and culvert hydraulics. And in my book, I have given a detailed design procedure for a guide month, how it is done. Anyway, that I thought I mentioned. And my email address, I wanted 14 papers. If you have any query, you can go through and you can ask questions, because I am an academic man, and if you have any query, I will reply to that one. Okay, thank you for giving me opportunity to.
I have shared the email ID of Majumdar sirs. If you have any query, you can mail directly. Thank you, sir.
Thank you, sir. Thank you.
Thank you. Thank you, everyone. And we can close the seminar for now. Okay.